Today, on how it's made. Heated skate blades. Gliders. Handbells. And fire hoses. Hockey skates are not all created equal. That's why professional hockey players are always looking for ways to get that cutting edge. They know championships are won or lost in fractions of a second. And that's when heated skate blades can make all the difference. With a simple touch, heated skate blades are revolutionizing the game of hockey. They give much more control and speed on ice. They do this using a smart board, the brain of these performance-enhancing blades. It all starts with custom-made stainless steel blades. A technician places them inside an injection molding machine. Liquid plastic is injected into a cavity, creating a plastic overmold. Once bonded with the overmold, the blades are ready to receive the electronic smart board. The smart board fits into the plastic overmold that runs along the top edge of the blade. After removing excess plastic from the mold, the technician places the prepared blades onto a mounting tray. He uses thermoconductive glue to ensure contact between the heating wire, the temperature-controlling smart board, and the blade overmold. After that, the technician inserts insulating material along the entire length of the overmold, so the heating wire makes perfect contact with the steel. Once the smart board is secure, the technician places the blades into a low-density injection machine that encapsulates the smart board with impact and moisture-resistant resin. The smart board is now waterproof. Meanwhile, another high-pressure injection molding machine makes the blade holders that support the finished blades. These blade holders will be given an actual power supply, a high-performance lithium polymer rechargeable battery that makes heating the blades possible. The battery will be cleverly concealed inside the heel of those molded chassis. To do this, a technician first attaches rivets into the heels of the blade holders, then mounts the blade holders onto an automatic rivet press. This machine pressure punches the rivets so they will make a proper connection to the battery for recharging. A printer heat presses the brand name and logo on the heel. The logo sits over the flexible proximity sensor, or the on-off button, that a technician wraps around the battery. Then she buries the combined unit into the heel of the blade holder to protect it from moisture and impact. She then locks it into place. Next, the technician attaches a threaded insert bolt to the blade overmold. This special bolt holds the blade in place and allows for quick and easy blade changing. The technician then connects the blade to the blade holder and presses the blade firmly into the chassis. Then she locks all electronic and mechanical components into place. A charging unit powers up the battery for testing. Then the technician seals off the heel chamber to further protect the battery. She turns on the smart board to make sure all systems are go. An LED confirms the blades are heating properly. In the meantime, another technician assembles the molded charging unit for the blades. The technician hand trims the motherboard that controls the charger so it will fit flawlessly into the charging unit. She inserts the finished motherboard into the back of the unit and checks to make sure it works properly. Then she snaps on an airtight cover that seals the unit, fully protecting the motherboard against wetness and shock. Finally, she plugs in the charging unit to confirm it works. A rechargeable battery, a manual, a convenient charging unit, and a pair of performance-enhancing skate blades complete the kit. The heated skate blades are now ready to ship around the world. They're quick and easy to mount on the boot, with the built-in smarts to help create the next champion. Gliding involves flying unpowered aircraft, though some models are fitted with a small engine and propeller, so they have the power to launch into the air on their own. No matter what the model, the sport of gliding is all about the joy of using the forces of the atmosphere to fly higher, faster, and longer. Gliders, like this model version, have three main parts: wings, fuselage, and tail. Workers build each part of the glider in two pieces, using resin and steel molds. They begin with the fuselage mold. They lay down strips of Kevlar, a strong heat-resistant material. Then they apply epoxy resin to the Kevlar fiber to reinforce it. They leave the epoxy to dry, and the next day apply strips of carbon fiber to reinforce the fuselage. The direction in which workers lay down the fiber layers is key. In flight, gliders are subject to strong forces that can bend and twist the structure. They must be sturdy yet as light as possible. The glider's tail boom gets the same treatment, except where the antenna will go, as radio signals don't penetrate the carbon fiber very well. Workers apply a thin coat of white gel paint to the 9-meter wing mold. Gliders are always white, so they don't absorb the sun's rays and overheat. They roll a sheet of carbon fiber over the painted mold. Then the entire assembly team skillfully applies an even coat of resin. They've got to be quick. The resin cures in just 30 minutes. They add a final layer of carbon fiber to strengthen a portion of the wing that's subject to strong wind currents. After laying a white fleece over the layers of carbon fiber, they seal it between two sheets of plastic. A vacuum compresses the layers, which draws excess resin to the surface where workers can remove it. The two wing parts are glued together using the same epoxy resin that bonds and seals the carbon fibers. Mixing in some cotton flakes helps thicken the resin, which they apply to the main spar, the wing's backbone, then to the front, back, and center portions. Using a crane, workers carefully fit the two wing molds together. The mold's weight forces out any excess glue. They tightly clamp the two molds together and leave them to harden overnight in an oven heated to 60 degrees Celsius. The next day, there's a loud pop when workers separate the two molds. They carry the completed wing structure, which weighs only 60 kilograms, over to another area to trim the resin overflow and sand down the seams. Using a diamond-tipped cutter, they cut the wing in two for transport, revealing its inner structure. Then they make sure they can easily put it back together before going on to the paint shop, where they reassemble it. Workers scan the surface and mark the areas they will sand by hand. They mount the glider's fuselage on a rotating stand so they can easily access the entire surface. They sand it and then polish it to a mirror finish. As workers assemble the glider, they inspect every system. They check the engine command that lowers the glider's launch propeller and retracts it into the fuselage. The landing gear must lower and retract smoothly out of the glider's undercarriage. Now they reassemble the wings. They check the air brake located in the wing. And finally, they install the canopy. The glider is complete. Sturdy yet light, this mid-size model can reach speeds of nearly 300 kilometers per hour, thanks to its sleek design. Handbells can be seen in church choirs, schools, and ring concerts. There, skilled ringers read music similar to a piano score, playing all the notes found on a modern musical keyboard. Finely crafted and tuned, handbells will continue to entertain generations to come. Handbells have a long tradition of making beautiful music, from church hymns to the music of Beethoven. It all starts with a casting mold that a worker encloses in a two-part container or flask. He fills the bottom half of the flask with special coarse sand that's ideal for making sand molds. He compacts the sand, and then he turns the metal flask over. He places guide rods onto the bell shapes and fills the top part of the flask with sand. He puts a ramming board on again, and he compacts the sand that fills the top part of the flask. Now he removes the guide rods. Then he removes the top half of the flask and takes out the casting mold. He reconnects the top of the flask and then frees it completely from the sand mold. A worker places bronze ingots into a crucible to melt them down. He places heat-sensitive material onto the sand mold and then heavy weights to hold the mold together safely. When the melted bronze reaches about 1200 degrees Celsius, a worker guides the crucible over to the sand mold and pours the molten metal into the cavity of the mold. He stops pouring when he sees the heat-sensitive material smoking. This indicates the mold cavity is filled. Workers then use a vibrating bed and small hammers to free the finished castings from the sand mold. Rotor blasting cleans the dirty castings. A worker trims off the excess pieces that fed the molten metal into the bell cavity. He sands the sharp edges of the bell and then drills the center hole for the assembly screw. The bell casting then goes on a lathe. Here, a carbide cutting tool, working with a stylus that follows a template of the bell, removes the coarse casting surface and makes the bell shiny. This turning operation also shapes the bell to give it the right tone. Another carbide cutting tool shapes the inside of the bell casting, giving it shine and the desired tuning as well. Using a custom-made tracing device, a worker reproduces the outside shape of the bell on paper. He then traces the inside of the bell casting until he completes an exact replica of the inside and the outside shape. This must match a master template. A worker polishes the bell using fine sandpaper. He also puts a jeweler's finish on the inside. Then he tests the bell's sound quality using a stroboscopic tuner and the human ear. He resands the bell to make a slight tonal adjustment. Then he tests it again to make sure it strikes the perfect musical note. A worker gives the bell the final polish, and another craftsman engraves the bell for the customer. Finally, a worker puts the ringer and bell together. She puts a washer, a hand disc, and a handle onto the assembly screw and screws it all into place. Handbells make wonderful music in the hands of skilled ringers. Whether the musical compositions are performed by an intimate gathering of friends or by a concert bell choir of 13 ringers or more, the music made by traditional handbells is timeless. Firefighting used to consist of passing water buckets hand to hand. The first fire hoses of the 1600s were made of leather, but these hoses were heavy, would crack when dry, and often break open under pressure. Modern firefighting began with a lightweight cotton fire hose, lined with rubber to keep the cotton dry and flexible. Fire hoses come in a range of sizes to fulfill a range of functions, from small lightweight ones for fighting forest fires to large heavy-duty hoses for industrial fires. Production begins with hundreds of bobbins of polyester yarn feeding automated looms a floor above. A series of spring rods keep the yarns under uniform tension. This is essential to create a tight weave. The factory programs each loom to weave specific patterns which incorporate identifier stripes. This is a visual guide to help workers assemble the fire hose later on. This woven fabric will form the fire hose's exterior, called the jacket. It's got to weather some nasty conditions, so they soak it in a plastic polymer solution with dye for color. The liquid encapsulates the fibers, making them durable and water-resistant. At another station, they mix granules of polyurethane, a form of plastic, with white colorant and adhesive pellets. This mixture is for making the waterproof tubing that forms the inside of the fire hose. When they activate the adhesive in the mixture with heat, this tubing will bond to the hose jacket fabric. The mixer feeds the ingredients to an extruder, which melts the mixture and forms it into a hollow tube. The tube then passes through a basin of cool water to set the plastic. Next, the tube goes to the inspection table, where an automated printer prints code numbers on it for tracking purposes. To assemble the fire hose, they first pull an outer hose jacket over a 30-meter long cable. Then, with another cable, they feed a second untreated hose jacket inside the first one. Finally, they attach a cable to the third and innermost layer, the tube, and pull it along the entire length of the double jacket. Once it's all the way through, they trim both ends. The three layers, outer jacket, inner jacket, and tube, are now ready to become one. They begin the fusing process by clamping one end of the assembled hose to a steam nozzle. As the clamp holds the hose steady, the nozzle blasts pressurized steam into the tube. At the same time, it moves backward, pulling out any kinks. The hot steam melts the adhesive in the tube material, and it penetrates the inner jacket around it. Once everything's perfectly straight, they pump in cold air to solidify the adhesive. This permanently bonds the layers. They roll up the finished hose into a coil, controlling the winder with a foot pedal. Then they lay the coiled hose on a table to install the couplings. Those are the components that attach the hose to the water supply on one end and to the spray nozzle on the other. They trim each end, then insert a brass expansion ring and an aluminum coupling on top. An expansion machine does the rest. They attach the end securely to the machine's protruding bar. Then the bar retracts and expands, pushing the brass ring outward. The force wedges the brass into the aluminum coupling permanently. This company tests every fire hose it produces under high water pressure on this table. After marking the type of hose with a stencil and indelible ink, they fill the hose with water. They check for holes and kinks and verify that the couplings stay in place. After the test, they drain the water. They insert a giant sponge to get rid of any water left behind. And now these new hoses are ready for their baptism by fire.